Welcome to another podcast. This episode we're going to be taking a look at how to find the Laplace transform of periodic functions. There are a variety of very important functions like sine, cosine, but more importantly, engineering uses these all the time. Functions like the square wave, the sine wave, the sawtooth wave, the unit wave, all these different kinds of periodic discontinuous functions. And so it would be helpful if we could have a nice formula for how to find the Laplace transform of a periodic function to help us when our inputs, especially in electrical circuit problems, are right-hand sides consisting of these types of formulas. I want to talk a little bit about what periodicity is, though, before we jump into this too far. You say that a function f of t is periodic with period t if when I add t to the function, I get back the function itself. It has no effect on it. Translating something by its period doesn't shift it. For example, if you look at the function of sine and you shift sine by 2 pi, you can't tell any difference. You get back the exact same function. What this involves then is something called the window of a periodic function. And so the window of a periodic function is defined as the function f sub t, where t is representing the period here. And it's the very first period, the first positive period of the function, meaning it's f of t for values of t between 0 and the end of the first period, and then the function is 0 otherwise. So if you think about this in terms of something like sine or cosine, you could think of the first period of sine as going from 0 to 2 pi. So if I was just to look at a graph here, sine would go from 0 to 2 pi. It would be something like this. And then we would go to 2 pi. And normally this would keep going on, but the period of the function being 2 pi means that we're only going to consider the function on that interval, and then its window would be zeroed out from then on. Now this is, normally it would keep going on, but the window is what I have drawn in the red here as the part that it zeroes out after the first part. So this is the window of the sine function. So this is the window of f of t equal to sine t. And so we would call this function f sub t for that particular problem. Now, it turns out that if you have a function f of t with period t, then its Laplace transform can be found quite remarkably simply by taking the Laplace transform of its window and dividing by the quantity 1 minus e to the minus ts, where t is equal to the period of the function. And this is where the Laplace transform of f of t, capital T, is equal to f of t. So two things going on here. First off is the formula that we have for the periodic function, and second is the formula we have for the window. So this is the transform of the window. And what the transform formula here for the entire periodic function says is that if you just transform the window of the function and then divide by the quantity 1 minus e to the negative ts, then you're done. And this is where t is equal to the period of the function. So that seems to greatly reduce the amount of effort that we need to apply in this case. I do want to go ahead and give a small proof of this result just so that you are a little bit comfortable in understanding some of the ins and outs of what's going on here. So the proof of this result comes from the fact that you can decompose a function into its windows, meaning that if I look at the function f of t, so I'm starting at 0 and going on, I'd have the first window, which would be f of t, plus the second window, which would be f of t shifted by t. So if I shift the first window period amount of t, then I'm looking at the second window. And so this would be from 0 to t. This would then take over from t to 2t. And then one more would be t minus 2t. So if I shift over 2 periods, then this is the function on the second to third period, and so on. That would completely describe the function as just a sum of a bunch of windows. And because these functions are 0 outside of their window, because each of these is a window, then adding in the Laplace transform, or not the Laplace transform, adding in the Heaviside functions at each step shouldn't affect the value here. In other words, if I write h of t times f of t plus the Heaviside function turning on at the next period, plus finally the Heaviside function turning on here after 2 periods, then these should be exactly equal, because I'm not changing anything, I'm just doing the exact same thing. Because these pieces up here fit together perfectly, then adding the Heaviside functions in here doesn't change anything at all. And what's nice about that is if I ask you now what is the inverse transform of this function f of t, then I can start taking inverse transforms of each of these pieces. And the inverse transforms of these pieces are pretty easy to find using this formula. If I take, or I don't need the inverse transform, I need the actual transform, sorry. If I take the transform of the window, it's just f of t times e to the minus 0s, plus here this is f of t as well, but here the shift is t, so it's e to the minus st. Here the shift is, actually I should probably do e to the minus ts, since that's the way we wrote the formula, plus another window, and we have a shift of 2t for this one, so it would be e to the minus 2ts, and so on. And if you factor out the window transform, e to the minus 0s is 1, plus e to the minus ts, e to the minus 2ts. You could see that the next one would be e to the minus 3ts, and so on. And what you hopefully notice is that this is a geometric series with r equal to e to the minus st. You can see it here. This is e to the minus st to the 1. This is e to the minus st squared, e to the minus st cubed. So it is indeed a geometric series, which we have a nice sum formula for geometric series. I would simply replace this sum in the parentheses with 1 over 1 minus r, and r is e to the minus ts. And so you can see here that the formula we end up with, this really nice formula here, matches what we proposed earlier as being the formula for a periodic function. So let me just go back and make sure that we understand how to apply this. All you do is you find the transform of the function on its window. And then once you have the transform of the function on the window, you divide by this 1 minus e to the minus ts quantity. Just to make sure that we're on the same page here, When I talk about the transform on the window, so maybe I'll just open this up a little bit more and add to it. When I talk about the transform of the window here, the window is simply the integral from 0 to t. I'm not going all the way out to infinity to take my transform. I'm going from 0 to the end of the first period. And so it's just a integral formula here that's involved. So that is the formula in this case. Of the transform of the window. So this is sort of an in-depth topic here. This allows us a great amount of freedom in what kinds of functions we want to have on the right-hand side of our differential equation. Do we want to turn things on periodically? How do we want to put together any kind of forcing function that we can think of? We now have access to discontinuous functions. We now have access to periodic functions and piecewise functions. We have access to just about anything you can think of. As long as it's of exponential order, we can take its Laplace transform now. And so this greatly increases the amount of viability that we have in solving differential equations subject to all different types of forcing functions. All right, thank you for watching.